So in this video I'm going to show you how to answer this worksheet that you got in class on the normal vector representation of a line using the calculator. There are lots and lots of things we can do on this worksheet that practice lots of the different functions on the calculator. So for the first one we need a coordinate system to plot some functions. So let's add a graphs application first. Our first function is minus 0.5x plus 2. So we can put this function into here, press enter, and then we have our line here. The gradient, hopefully you remember, is how steep the function is. And I can read off of here that the gradient of this function is minus a half, or I could create a triangle here, and I see that this would be then 2 and 4, 2 divided by 4, and of course that's in the negative y direction, so negative 2 divided by 4 would give me a half to be the gradient. And the y-intercept is where the function crosses the y-axis, and we can see quite clearly here it crosses the y-axis at y equals 2, which you should also have been able to predict from this 2 at the end here. So that was a little bit of revision. Now we have an explicit equation that we need to convert into its implicit form, and hopefully, let me make this one a little bit bigger now because we don't need the calculator for that. Hopefully you remembered that the implicit form was in the form ax plus by equals c, where a, b and c are whole numbers. So in this case, if I multiply my equation by 3, I get 3y equals 2x plus 12. And then if I take 2x away from both sides, I would then get 3y minus 2x equals 12. And that there is in its implicit form. If you've forgotten how to do this, or you've forgotten the context in which we learnt it, page 195 gives you a little hint there, or you can read through those things again. But it's just, equals, sorry, not plus. It's just that you have integers before the y and the x, and they're both on the same side, and you have another integer that's on the other side. So that's part 2 done. Part 3 says check by calculation and graphically whether these 3 points lie on this line. So let's do this graphically first. So menu, graph entry, edit. And if I want to add in an implicit equation like this one, I can use some of the equation templates on the graphing application. So I know that this is going to be a line, and it gives me a couple of different forms, and the form of this one, 2x plus 3y equals 5, is similar to this line form, so I'll click on that one. So I get 2x plus 3y equals 5, and then I can draw that line there. And I can see on here if 1, 1 lies on this line. So if I hide the function that I'm not interested in, I go menu, graph entry, edit, and I entered that in the function one. So this function here is the one that now I'm not interested in. So I've hidden that one, and I'm just left with the line that I am interested in. And I can go menu, trace, graph trace on this one, and if I press the arrow keys, this one here and this one here, I can move along the function, and I can see that it kind of looks like 1, 1 lies on the line. If you want to check by calculation, you put 1 in for x and 1 in for y and see if you get 5 out, and the same for the other 2 points, the x value in for x in here and the y value in for y in there, and see if 5 comes out. Let's do then number 4. We have 2 equations in each one, and we need to find the point of intersection of the following lines, both by calculation and graphically. So let's go to our equation templates again to insert the first one here. What I'm going to do before I insert that is I'm going to hide this one because we're no longer interested in that one. Here I have 3x plus 4y is equal to 11. and then I'll add in the other one, which is also in this form, 5x minus 5y is equal to 9. And I see that one goes like that. And it can tell me the point of intersection if I go Menu, Analyze Graph, Intersection, and I set my lower bound before the point I'm interested in, and my upper bound after the point I'm interested in. It tells me that the point of intersection is 2.6, 0.8. So that's how you can do it graphically. I'll leave the other one as an exercise for you to do graphically, so you can see how to do that yourselves. For the other one though, to make sure you have the correct answer, I'll show you how to do this by calculation. So let's open then a new tab, calculator tab, and for these two equations here, both dependent on x and y, the point of intersection is where the x coordinate and the y coordinate are the same for both lines. So we need to find out the x and the y that would be the same for each of these. So when these two expressions are kind of equivalent. And hopefully you remember from last year, this is the same as solving a system of linear equations in x and y. So I can open my book, I can go to tab 2, and because our calculator is very handy, I can go to Algebra, and I can solve system of equations, solve system of linear equations, two variables, x and y, two equations, okay, and then I can just type them in. So the first one is 4 is equal to minus 2x plus 10y, and the second one is y is equal to, control, enter my fraction, 2/3 x plus 8/3, again with a fraction. Enter, and you see here, this is the value that comes out for x, minus 34/7, which of course you can convert to a mixed number, and this is the value that comes out for y. So then we've done the warm-up. Now we come to our new information. First of all, I need to draw this line here, 2x plus 3y is equal to 7. So I can go back then to my calculator, and I can go back to my graphing application here, menu, graph entry, edit, equation templates, line, this style of line, and that's E4 now. 2x plus 3y is equal to 7. I can get rid of E3, I can get rid of E2, but of course they're still there in waiting if I need to sort them out again, or call them up again in some way. So we have this line now here, the one in pink. Ignore this point here, that was our intersection point from the last ones, which I could delete, but I won't waste time doing that. So we know that every line can be defined as a linear function. Every line can also be thought of to have corresponding direction vectors and normal vectors. So these two representations of the line are connected. So you're familiar with the linear function way. And now I hope to make you become familiar with the direction vector way and the normal vector way of representing the line. And this sheet works with the normal vector representation of the line. So we need to figure out how the normal vector representation of the line is connected to its linear function. So for this line G that we drew in one, please correct that on your sheet, we need to find a direction vector and a normal vector. And here we have a hint. You can choose 2 points on the line, A and B, to find the direction vector. So the coordinates of A and the coordinates of B. The direction vector AB would be B minus A, for example. We can also just read it off. This one here. So if I choose a point on the line here, I can see how many I would need to go along and down to get to another point on the line. And if I choose, for example, this point here, which would be 2, 1. And I know I also have one at 5, -1. If you go to Menu, again, Trace, Graph Trace, you can see which ones have whole number coordinates, or of course you could use this. But I've used the points 2, 1 and 5, -1. I've taken one away from the other to get the direction vector of 3, -2. So we had 3, -2 for the direction vector. This is just a vector that goes in the same way as the line does. So I go 3 along, -2 down to get back onto the line. The normal vector is perpendicular to this one. And you know, if you want to find a vector perpendicular to this one, the easiest way of doing it is by flipping the components and making one of them the opposite sign. So here, -2, 3 is after it's flipped, and then changing the sign of 1, let's make the -1 positive, we then have 2, 3. And hopefully you notice that the components here of this normal vector, n, are identical to the coefficients of this implicit equation. So we have 2, 3, 2, 3. You should check this then for 2 further examples in the warm-up section. I'll leave that as an exercise for you. And it kind of leads us on to our new knowledge, that if a line G is given in its implicit form, ax plus by is equal to c, then the normal vector of that line has components a and b. Also, the scalar product of this normal vector and any point on the line, so the coordinates of that point, results in the number c in the implicit equation. So if you have AB and then a point on the line xy, AB scalar product xy will give you that number c. So we can rewrite the equation of the line as this. Any point on the line can be substituted then for x. So x is the unknown in our equation, and it's normally written with a normal vector that you found and a constant c you found by completing number 4. So if we had 2, 3 like we found up here, and you choose a point on the line G, then one point on the line would be 2, 1. 2 times 2 is 4, plus 3 times 1 is 4 plus 3, which gives us 7, which is, as I've said, this constant here. I'd like you to practice this part on your own. You'll be doing mixed exercises with the group who's become experts at this on Friday. So it's quite a lot to take in 15 minutes, but hopefully this has given you an introduction so that you can start with a good basis to see what the other group has done. I also hope it's given you good practice at using several different functions of the calculator, so you can start becoming a lot more familiar with all of the different applications. The way to get good with the calculator and get fast and have it as a tool that can really help you in exam situations is to use it as much as possible. And you see in these examples, it really meant that we could do things much faster than just doing everything by hand.